Okay, now we can actually integrate some functions that lead to inverse trig functions, since we know the derivatives of certain inverse trig functions. So let me give you three formulas here that you can use for integration. The first formula, if you want to integrate du over the square root of a squared minus u squared, that's going to integrate into arc sine of u over a plus a constant. So an example of that would be if we wanted to integrate 2dx over the square root of 9 minus 4x squared. Now, notice here that the denominator has a square root, and 9, now it doesn't have to be a perfect square, because even if that was 8, we could say a was the square root of 8, but a would actually be the square root of this constant, so a would be 3. U, since this is 4x squared, we would have to treat u as the square root of 4x squared, which is 2x. And then if u is 2x, then du is pretty much locked in. Du has to be 2dx. So we actually do have this in the proper form, because if you look at that now, the top is du, 2dx is du, and the bottom is actually the square root of 3 squared minus u squared. So if we were to integrate this, we could just use this formula. It's going to be equal to the arc sine of u over a, and in this case, remember, u is 2x and a is 3, so it would be the arc sine of 2x over 3, and then plus a constant since it's an indefinite integral. Now another formula for this would be if you're integrating du over a squared plus u squared, that's actually going to be equal to 1 over a times the arctan of u over a plus a constant. So let's take a look at something like that. So let's look at this and see what we can do with this integral. Well, first of all, 5 can be treated as a squared, where a is square root of 5, because if you square root of 5, you get 5. And x to the fourth can be treated as u squared, where u is x squared. But if u is x squared, then du is 2x dx. So what I'm going to have to do is, in order to get a 2 up here, I'm going to have to multiply the numerator by 2 inside the integral. And remember, I can do that as long as I multiply on the outside by 1/2 of that. So now, here's what I've got. I've got 1/2 on the outside, and now that integral is of the form, the top is du, right? And then the bottom is simply square root of 5 quantity squared plus u squared. And so it fits this form up here. So now it's just going to be 1 over a. Well, it's going to be 1/2 times 1 over a, but 1 over a would be 1 over square root of 5. So if you take 1/2 times 1 over square root of 5, you're going to get 1 over 2 square root of 5. And then you're going to have arctan of u over a, but u is x squared, and a is square root of 5. So you get 1 over 2 square root of 5 times arctan of x squared over square root of 5 plus a constant. And so that's the answer for that example. Now, if you have an integral in this form where you have du over u times the square root of u squared minus a squared, it integrates to 1 over a arc secant of the absolute value of u over a plus a constant. So let me give you an example of that one. Okay, so on this one, if you'll notice in the square root, 16 can be thought of as 4 squared. So I would have 4 squared, Okay, I had my example written backwards there, so I had to fix that real quick. Alright, so actually this integral is, if you look in the denominator, you've got the square root. If you let u be 3x squared, then 9x to the fourth represents u squared. And then out here we have u, which is, 3x squared. And then here we have 4 squared. So a is 4. But the deal is that if u is 3x squared, then du is 6x dx. So what I'm going to have to do, so that this top is going to be du, I'm going to have to multiply up here by 6 and on the outside by 1/6. And that will fix that. And now here's what I'm going to get. So now the 6x dx is the du. I bring the 1/6 on the outside, and then the 3x squared is the u, and then inside the radical I have 9x to the fourth, which is u squared, and then minus 16, which is 4 squared. So now this looks exactly like this up here. So now I can use this formula, and remember I have 1/6 here, and then I'm going to have 1 over a, which is going to be 1 over 4 arcsecant of the absolute value of u, where u is 3x squared. And actually you can remove the absolute value here because 3x squared can't be negative. And over a, so I have over 4 plus a constant. And then you can multiply the 1/6 times the 1/4 and make that 1/24. So you get 1/24 of the arcsecant of 3x squared over 4 plus a constant. Now there's other examples where you might have to do some work to put it in the proper form. Here you'll notice I have the integral of dx over x squared minus 4x plus 7. Well, I can actually complete the square here. If for x squared minus 4x, if you take half of -4, you get -2, and then you square it, you get 4. So what I can do is I can add 4 to the first two terms and then take 4 away from the third term, and then what that'll give me is, now this will be a perfect square, so that's x minus 2 quantity squared plus 3. So now if I let u be x minus 2, then du is simply dx, and a is square root of 3. So now I have the form du over u squared plus square root of 3 squared. And you don't actually have to switch here, but I did. So the formula for du over u squared plus a squared is actually 1 over a arctan u over a plus a constant. But we know that u is simply x minus 2, so just replace u with x minus 2, and there you go. So there you have your answer there for the integral. Okay, now here is a function, and we want to find the area bounded by this function, the x-axis, from 3/2 to 9/4. Now you might want to check the graph first to make sure it's non-negative, but it is. So I'm going to go ahead. Let's work outside of the integral to complete the square. Well, 3x minus x squared, that's the same as minus x squared plus 3x. So let me factor a -1 out of that. Now when I factor a -1 out of that, I get a negative times x squared minus 3x. Now if I take half of -3 and square it, that would be -3/2 squared. That's going to give me 9/4. So then I can put a 9/4 here, and then actually if you think about what I did, I actually didn't add a 9/4. Remember, this has a -1, so technically I subtracted 9/4, because -1 times 9/4 is minus 9/4. So to keep it equal, I have to actually add a 9/4 out here. And now so you have minus, and so this is the square root, this is minus x minus 3/2 quantity squared plus 9/4. And 9/4 is the same as 3/2 quantity squared. Now that can be written as 9/4 minus x minus 3/2 quantity squared, or 3/2 squared, minus x minus 3/2 quantity squared. So I'm going to replace this 3x minus x squared with what I came up with here, which is 3/2 quantity squared minus x minus 3/2 quantity squared. Now if you let u be x minus 3/2, then du is simply dx. And so what you're going to get is, and a of course is 3/2. Well, if you go back and look at your formulas, you'll see that this actually transcends into an arcsine formula where you have arcsine of u over 3/2. And arcsine of u over 3/2 would be the same as 2/3 times u, and since u is x minus 3/2, I can replace this with u with x minus 3/2. Now, what you want to do is you want to evaluate this from 3/2 to 9/4. See, I switched it back to x, so I don't have to do, I didn't change the u values for my limits. So I'm going to integrate from 3/2 to 9/4. So basically plug 9/4 in, and I get arcsine of 2 times 9/4 minus 3 over 3, and then minus the arcsine, and you evaluate it at 3/2, 2 times 3/2 minus 3 over 3. And that's actually going to be arcsine of 1/2 minus arcsine of 0, and arcsine of 1/2 is pi over 6, and arcsine of 0 is just 0. So your answer is just a simple little pi over 6. Okay, here are some similar problems. I'll let you freeze the video and look at this one if you want to, but this leads to arcsecant. This one, actually this one, you can use the power rule on this one, so you don't actually have to use the trig identity on this one. So you can just use the power rule here, and it works out nicely with the power rule letting u equal x squared minus 1, and so you get u to the 1/2 du, and you do have to manipulate it some because you had to put a 2 in and a 1/2 on the outside. This one we don't have the tools for because we don't have, this one doesn't fit anything that we've learned. Here's one where we can use the log rule. I think I showed you one similar to this earlier. And then this one we can actually use the power rule because here you actually are going to have, this is actually just going to be u du, because if you let u be natural log of x, then du is just going to be dx over x. So you're just going to get u du, and then you can use the power rule and get u squared over 2 plus a constant. And u is natural log of x, so you do that. We don't have the rule to do this one yet, even though there is a formula for the natural log of x, but we don't have the tools yet for that. And then because what you have to do is you have to use integration by parts, which I'll talk to you a little bit later about. But basically, if you did integration by parts, you could actually integrate the natural log of x dx and get this function. So these are just a few problems that might look similar to one another. These top three, of course, look similar, but one you can use the inverse trig rule, one you can use the power rule, and then of course this one we don't have any rule that we can use. See, the problem on this one is you might think, well, I could let u equal x squared minus 1 and do it as a power, but when you do du you get 2x dx, and we don't have an x up here in the numerator, so that's not going to work. And that also doesn't fit any of our inverse trig rules, so we don't have the tools to deal with that one yet. So I just wanted to show you these three that look similar and these three that look similar that require different rules to approach them. And now I'm going to leave you with the table of basic integration rules that we've talked about so far, and you can use a camera, or your phone, take a picture of these, or you can just pause it and do a screenshot. But these are the basic integration rules that we've covered up to this point. Believe it or not, there's another class of functions I'm going to talk about next called hyperbolic functions.